applying for this student council scholarship, and I was wondering if you could fill out the teacher equity form.
Sure.
It's due like 25th, so it's not anytime soon.
Okay.
So I have to do it right now.
Okay. Just remind me, because, like, nag me.
Okay.
Yeah, if you're like, Ms. Spence, have you done it yet?
Okay.
Yeah.
You don't have to give it back to me, just give it to Mr.
Okay, cool. Alrighty, my friends, we are going to hopefully wrap this up today. Probably not, but we'll get close. It's fine. Yeah, don't worry. Okay, AP Chemistry, here we go. When last we spoke, does anyone have any questions on anything, by the way, from previous? We're doing okay? Okay, we were talking buffers, yes? Remind me, what is a buffer? Tell your partner, what is a buffer? What do you need to make a buffer? So what is a buffer? What would you need to make a buffer? What is a buffer? It's a solution that resists a change in pH. When a small amount of acid or base are added. What do we have to make it with? Pardon me? We're going to make it with a strong acid or base. So if I had HCl, and in my solution, it dissociated. So here, I have a beaker. Wow, that's a weird line. I have a, what is it doing? There, that's better. I have a beaker, and it contains H+, and it contains Cl-. What happens if I add some HA, or let's say HBr, add some HBr? Is it able to use up the extra H+? No, why can it not use up extra H+? Because it cannot shift that way, right? So can't use up the extra H+. We're just going off script. Off script, okay? So not a strong acid. Okay, so made with not a strong acid. Or strong base for the same reason. So if it's not a strong acid or a strong base, what is it made with? Made with weak acid. So is it okay to just have weak acid? So if I had a weak acid, HA, okay, I did not do that. Like the pen is like got a mind of its own. So anyway, it would look like this: HA, 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 Okay, because mostly weak acids are what? Undissociated. Yes? So now if I add some H plus to that, yes? Here comes my H plus. Those two would react, yes, and form HA. Now what happens when I add my next H plus? It can't do anything with that H plus, so the H plus concentration would increase. So a weak acid on its own will not make a buffer. Because it can't, you know, sop up that extra H plus. What should we make it with? Let's try a weak base. Okay, so I've got B, 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 and I have a little bit of HB, right? Because B plus H2O gives us BH plus plus OH minus, yes? So this is there we go. So if I add hydrogen to this, what would happen? Would adding hydrogen work? Yeah, adding hydrogen would be okay. Adding hydrogen is okay, right? Because we would have B plus H plus gives BH plus, yes? Okay, what if I now add some sodium hydroxide? So I add 1 hydroxide. That's going to get together here, yes. And I'm going to make B, and I'm going to make H2O, yes. The next hydroxide I add, what happens? Nothing, right? I just have more hydroxide. Now my pH is going way, way up, yes? So also not on its own. So you can't make it with a weak acid all on its own. You can't make it with weak base all on its own. What can you make it with? Sorry? Both. Weak, weak. It's a weak acid. So you have to have both. You have to have both the weak acid and the weak base there, because if we do that, right, now I've put some HA in there. I've also put some A minus in there. That's going to be from maybe some NaA. Yeah? Okay. So now I have lots of HA because I've added HA. But I also have lots of A minus because I've added a bunch of NaA. Yes? So I have lots of both of them. So now if I add hydroxide, what's it going to do? That's going to react with my HA. Yeah, and that's going to then give me A minus plus H2O. So have we affected the concentration of hydronium very much, or hydroxide? No, because we had something for it to react with. We have, if you add OH, there is a weak acid for it to react with. What if we add H plus? It's going to react with the A minus, so I'm going to add some H plus. It's going to get together with the A minus and make HA. So now I don't have any extra H plus, so my pH is staying relatively stable. Yes? So you need to have a weak acid and you need to have the conjugate weak base. You cannot get A minus on its own, so you need to combine it with a positive ion in the form of a, what do we call that kind of a compound? That's a salt. So that is the salt of the conjugate base. Yes? I can even print out these notes if you want. Right? Like I can do that during our break or whatever, if you'd like. Okay? So, a buffer. Buffer composition. Two options. One, Wascaba. That's a weak acid and the salt of its conjugate base. And the second one, Wubska, which is a weak base. And the salt of its conjugate acid. So for our weak acid and a salt of its conjugate base, you could have, for example, HF and what would we put with it? NaF. And you're always going to pair up that ion with something that's like pretty non-reactive. So who's your best choice? Our good friend, sodium. Okay, you could choose potassium. You would not want to use, say, ammonium, because ammonium is itself a weak ammonium. Ammonium is a weak acid, yes? So you would want to choose something like sodium or potassium, perhaps lithium. Don't go any crazier than that, okay? And then for a weak base and the salt of its conjugate acid, these don't come up very often because there's not a whole lot of weak bases that are just like a base without a charge. Okay, so we have NH3, and what is its conjugate acid? NH4, right? NH4 plus. Who should we be pairing that with? There are actually quite a number of choices here. You could choose any of the CL or BR because CL or BR or NO3, what do all those have in common? They're very soluble. Okay, so you're not going to get any weird reactions that you don't want. But what else? They're all conjugate bases of strong acids, so they're too weak to act as bases. They're neutral in water. None of these. What's the word if they are neutral in water? Okay. We're good. Because I'm recording locally. Okay. Okay, so none of these do what? React with water. So they are neutral in water. What's another way I could say that instead of saying react with water? Hydrolyze. None of these hydrolyze. Okay, so they're all going to be neutral in water. So you want to pick something that's not going to hydrolyze, something that's not going to form precipitates with all and sundry. Okay? So those are the compositions of a buffer, and for the regular exam, that's pretty much all you need to know. Okay? So you need to know that buffers keep the pH relatively constant, and you need to know that you can make them from a weak acid and the salt of its conjugate base, or from a weak base and the salt of its conjugate acid. The other thing you need to know is that this one buffers best if you want a buffer that buffers above pH 7. Generally, you will be using a weak base and the salt of its conjugate acid. Why am I highlighting that? Above pH 7. And this one you're going to use when you're using the weak acid, you're going to use it to buffer below pH 7. Now, you can change those things depending on the strength of the acid. Sometimes you can get it going the other way, but those are just sort of generalities. That is for your regular exam, okay? For the AP exam, you should know weak acids and their conjugate bases are best at buffering close to their pKa value. Okay? Okay? So let's say I wanted to buffer at pH 5. I would like you to go find me a pair of substances that would buffer nicely at pH of 5. That's so weird. Oh no, it's not. I'm just, my brain is, no, my brain is weird. It's okay. Did it? What do you guys think? Anyone got a suggestion for me? H what? HC, hydrogen chloride? Sulfide. Hydrogen sulfide. Okay, so hydrogen sulfide, H2S, has a Ka value is equal to 9.1 times 10 to the negative 8. What would its pKa be? How do you calculate a pKa? Negative log of Ka. And assuming that we don't want to like spend too much time doing the math here, because we're just saying approximately, what would the approximate pKa be for this substance? It's going to be about 7 or 8, okay? It's because the 9 is close to 10, you might say it's closer to 7, okay? So the pKa is probably approximately equal to 7, okay? But even if you said 8, you know, it's close enough to know that is that going to be the good choice if we want to buffer at pH 5? No, because we want something to buffer with a pKa value of close to 5. What could we choose? Acetic acid. Yeah, why not? CH3, COOH, our Ka is 1.8 times 10 to the minus 5. Therefore, our pKa is going to be approximately 5. Okay? So that looks like a really good choice. Yes? No, it could be an ion. So you could, for example, choose the dihydrogen citrate ion. Okay? Huh? It can be. We're going to get there. We're just kind of dealing with the acid situation right now. Okay? So what we have here is we got an acid here. And what else would we have to do with this acid? Would this be a good buffer? We need its conjugate base. So who is its conjugate base? CH3, COO minus. Is it okay to just leave it like that? Nope, it needs to become Na, CH3, COO. Okay, so this would be a good choice. We could also choose the dihydrogen citrate ion. And in fact, I'm going to choose a different one. I'm going to choose the, oh, no, that one's fine. It's just got kind of a big formula, but that's okay. H2, C6, H5, O7, minus. And its Ka is 1.7 times 10 to the minus 5, so its pKa will also be really close to 5. And so that is also a good choice. Now, when we have this, we would need to say, could we just add that as it is, or what would we have to do with it? We would have to pair it up with Na, C2, H6, H5, no. sorry, Na, H2, C6, H5, O7. Oh my God, what have I done? No, that's okay. That's okay. That is correct. It's just really long, so it makes it look really weird. And what else would we have to have? The conjugate base. So who's the conjugate base? H, C6, H5, O7, 2 minus. So we would have then Na2, H, C6, H5, O7. I don't know why I wrote the 2 minus. Shouldn't be there because they've got the Na. So this would make our buffer. Okay, and this would make our buffer. Those two together. Now you have to have significant concentrations of these. For significant concentrations, that was probably like at least 0.1 molar. Okay. To buffer effectively. So if we did not have enough of one or the other, what would happen? It would what? It wouldn't be a good buffer because it would be like when you just had the acid and you ran out of the conjugate base like after no time at all. Yes? And that's why you have to have large, significant concentrations, probably 0.1 molar or more. But you will see questions where there are buffers that have 0.05, things like that. You know, they work best. Buffers work best when the two concentrations, they're the sort of easiest to work with when the two concentrations are equal. Okay? Or close to equal. When the two concentrations are large and approximately equal. Okay, so 0.1 or more, but like I said, you will sometimes see concentrations smaller than that, and it is still considered a buffer. It's just a buffer without as good of a buffering capacity. It will hit its limit, it will run out of either acid or base sooner than you might want, okay? So that's what they mean by buffer capacity. How much acid and base can you add before it stops buffering, before it stops keeping the pH close to where you want it? I made this whole worksheet. I spent a long time on it, and now I'm just writing everything. I don't know. I feel like this is somehow easier. Yeah. Anyway. When you run out, pH change will no longer be minimized. Okay, and that's what that all comes down to. Now, AP buffers. You actually need to do calculations with AP buffers. Okay? I'm going to give you like a quick and dirty version, and then I'm going to send you home with like a thing you can read that shows you like how you can do it another way. Okay? There is an equation. It is called the Henderson-Hasselbach Equation. What? Have you heard of this before? Henderson-Hasselbach? Oh. It was really funny. You used to have this PowerPoint presentation that I found for somewhere. Do you guys know who David Hasselhoff is? He was like in Baywatch, like that terrible show from a really long time ago. Anyway, I don't have it anymore because it's no longer funny because he's no longer like people just don't know who he is. But it was so funny because it would like literally would say like the Henderson-Hasselbach equation, and then it would like flip back and forth between the picture of Hasselbach and Hasselhoff, and like he would just pop up there. There's David Hasselhoff. Anyway, you were going to ask. Yes. At all. Yeah. Well, once you run out, you're done. Sorry, just gonna shoot up. No, they make it minimal. So, what would happen is that you would have if you have no buffer, your pH is going to go like this. Or actually, it would go down. If we add acid, it's going to go down really fast. Woo! Okay? Or actually, let's say we're adding base. Let's say we're adding base because that's easier to draw. It's going to go up really steep. Steep. Up. Yes? This is no buffer. But if we have a buffer, what's going to happen is our pH is going to go up slowly. And then all of a sudden, this would be base added. All of a sudden, we run out of HA. And it will literally go like this. Okay? Boom. It just goes straight up. Yeah? It's just smallish. Yeah. Yeah. Okay. So, where were we? We were talking about the Henderson-Hasselbach equation. And this is a lovely equation. It's actually fairly easy to remember. There are two versions of it, but it is also on your data sheet. Do you have your AP data sheet with you? So what we've got, let's see if you can find it. See that one there? It's in your equilibrium section. That is the Henderson-Hasselbach. Often referred to as the HH equation because nobody wants to write out Henderson-Hasselbach all the time. Okay, and it is for buffers. So you're going to take your acid, you're going to find its pKa, and then it is plus the log of the base form over the acid form. You see how it's A minus over HA? That's the base form over the acid form. So I like to remember it this way because somebody taught me this once. pH is equal to pKa plus the log of Ba. That's my B, and that's my A. So it's pH equals pKa plus the log of Ba. Yes, but you don't need to memorize it because it's there. But I thought I would tell you that in case you get to university and they don't give you a formula sheet and you need to memorize it. Okay? So going back. Where did it go? Here. There we are. Okay. pH equals, what's the formula again? pKa plus the log of Ba. Yes? I like writing it that way just because that way I don't have to remember quite as much, but pH is equal to pKa plus the log of A minus over HA. Yes? Now, there is a converse to that. Can anyone guess what the other one is? POH is equal to pKb plus the log of acid over base, AB. Yes? So this is the ABA equation because it's pKa equals log of B over A, ABA. And this is the BAB. Okay, you got the ABA and the BAB. Yes? So you can calculate the pH anytime you want. Now, the nice thing is, you remember how I said it was really nice if those concentrations were equal to each other? Yes? If the concentration of A is equal to the concentration of HA, then what is true about that equation? pH is equal to pKa and POH is equal to pKb. So rather than it just being close to the Ka and the Kb, it actually is the pKa and the pKb. Okay? So if HA equals HB, then pH is equal to pKa plus the log of 1, which of course is pKa plus 0. So pH is simply equal to pKa. Yes? Huh? Because you've got a conjugate acid and you've got its conjugate base. You can do it using a rice table. And absolutely you can, but this is faster. Do you know what I mean? Yeah, so if you wanted to do it using a rice table, you could be like, okay, well, let's see, I have, so in fact, you don't need to know that equation at all. You can just use rice. So if you have HA, H plus, A minus, you can use rice to find the pH of the buffer. So let's say that you put 1.0 molar HA in that container. Yes? You also put 1.0 molar A minus in that container. What's the initial concentration of H plus? 0. So this is going to shift this way because I have to shift towards that, yes? What can you say about these? They are approximately equal to each other because we're going to assume in both cases that X is insignificant. Why will I not get my red pen? There we go. Right? And if we do that, then what we get is we get Ka is equal to H plus times A minus over HA. Yes? And now we have, if these two are, if that's 1 over 1, in fact, I'm just going to leave it, or did I do that right? Yeah. Yeah. So you've now got Ka is equal to, the H plus is equal to, yeah. So if that's a 1, and if that's a 1, then you've got Ka is equal to H plus. Now, you might end up with numbers where these are a little bit different from each other, and then it's not going to be like Ka is equal to just H plus, right? But yeah, you'll still end up with something that's close to H plus is equal to Ka. Yes, yes? Okay. But if you use the Henderson-Hasselbach, you do not need to show a race table. If you use this, you need to show a race table. Yeah? Okay. Let's try one. What is the pH of a buffer solution consisting of 0.0350 molar NH3 and 0.0500 molar NH4 plus? I would like you to try it, solving it with the acid Henderson-Hasselbach and the base Henderson-Hasselbach, okay? Thank you. And if you're interested in that kind of thing, on this sheet there is a derivation of the Henderson-Hasselbach, so you can actually see like the log rules and how you can work through that. We're not going to spend much time on that though, because we've got like 2 weeks till the exam. I don't even have to write it and I'm having a heart attack. I don't know how you guys are doing. One day at a time, that's so smart, because you can't do anything more than that. Yeah, no, just one day at a time. Just do what you need to do today. You're so smart. That's so wise. Like, there's no real reason that you would do it this way unless you were like given a PKB or like given a KB first. Like, you would never be like, oh, I've got a KA, I'm going to use that second equation. That sounds like fun, right? You would never do that. I honestly don't think on the AP exam they're going to give you something where they give you a KB. But you know, you can always you can always swap it around. If they do give you a KB, you can find the Ka of the conjugate acid and then use that one. Yeah. Those are the notes that we just kind of did. And so the answers for these are on there. If you want to check them, they're on page 2. You can see there's a little sheep there holding chemicals. I was so happy to find that. pH equals pKa, best log of Ba. And then if you are interested in seeing how you would do it with a rice table, that's on the last page of that. I haven't got a problem set for this one because I could not get it together in time. So, you know, but I think you've got enough on your plate this weekend that we don't need a problem set on that one. So how are we doing with that? Are we needing more time or are we good? Are we good? Okay, good. Since we are done with that, we are now moving on to titrations. And I know you guys are really good with the titrations. Once again, there is a list of videos here, 5.6a. You don't actually need to look at this, but it is on page 68. I actually taught this in 2020 online. You know, when we went into COVID and we were all at home, I taught this online. So these are the videos from 2020 when I was teaching it. So you can avail yourselves of those if you wish to. Or of course we do have, and there's a lot, like it's quite a lot of stuff. Yes, you can see 23 minutes, 13, 22, 20, 29, 21, like there's a lot to it. But, oh, and then we have 39, and then we have going over a question from the Titration Curves worksheet. We're going to try and do it in a lot less time than that. Colger has, of course, his nice little 7 to 8 minute videos, right? So we're all good there. But if we go to 5.6b, we are going to look at this. This is on page 70, 70. Are we good? So this is on page 70. Do we all remember what an equivalence point is? The moment you go from having this in excess to having that in excess, the moment when those two things perfectly fulfill the stoichiometry of the reaction. If you needed 1 to 1, they are 1 to 1. If you needed 1 to 2, they are 1 to 2. Everybody has reacted and there is no excess of either. So you can look at that and you can see, you can have an indicator indicate when it changes color. That's like the titration we did last year, okay? Or you can have a pH meter and you just stick it in there and you just have the little bar spinning. Okay, there's like a magnetic stir bar at the bottom and you drip it in and you watch the pH change. And if you're really lucky, this just hooks up to a computer and plots it for you as you go, so you don't have to like take readings and then, you know, plot the whole thing by hand. It's super nice if you can just get it to do it automatically for you. So what is our go figure? In which direction do you expect the pH to change as NaOH is added to the HCl solution? Up or down? Is pH going to increase or decrease? It's going to increase, yes. Increase, excellent. Let's get a pen that works. Increase. Here is our little picture here of our burette, our titrant, our analyte, which I think I've been misspelling. I think I've been spelling it analyte, maybe? But that looks so wrong. I don't know, like it is analyte, not, anyway, I feel like I've been saying it wrong, but maybe spelling it right, I'm not sure. Anyway, it is analyte, okay? The equivalence point, the point at which the titrant added is just enough to completely neutralize the analyte. Our indicator changes color if you choose the indicator correctly, which we are going to focus on in this worksheet as well. It will change color when the equivalence point is reached. It is possible to badly choose an indicator and it will change color like 10 milliliters before you reach the equivalence point, which would be absolutely useless. It's like your reaction's not done and it's changed color and you think it is over. Yes? So you have to choose your indicator for your reaction well, and that's one of the things we're going to learn today. So we have an equivalence point, and sadly there's another thing that sounds very much like that. There is an end point. Thank you, Casey. The end point is the point at which the indicator changes color. And what you're looking to do is you are looking to make the equivalence point and the end point match up with each other. You want them both to happen at the same time, okay? When are we having our break? When do you want your break? Want your break now? Okay, we'll have a break now. If you are leaving early, there are acid and base review things here. So the ones that say applied practice, those are like old AP questions with explained multiple choices. Okay? Actually, they're not really old AP questions. They're from back in the day when somebody made a book that had old ones, like that had really good questions that explain things. So there's that for acid base 1 and for acid base 2. And then I just have the regular acid base 2 review as well. Okay? So you can help yourself to those 3, and then you can go on break, and we will come back at, what, 10 to 2? 10 to 2? Yes? 1:50? Back at 1:50. And I paper clipped them for you because I thought there were so many papers it was confusing. So yeah, the key is with the questions. Yeah. but they're separate so you don't have to like flip, flip, flip. If you would prefer to staple them, you can borrow my stapler. Okay, so a titration curve, remember we have a pH meter, we've stuck it into our solution, and if this is on our y-axis, the pH of the analyte solution, and remember, where does the analyte go? It goes in the flask, yes? So what kind of a substance do we have in our flask if this down here is our initial pH? Yep. What kind of a substance do we have? Yeah, so we've got an acid in here. And you'll notice as time goes on, what is happening to the pH? It is increasing. It increases slowly, yes. And then we have an inflection point, and then where it changes very, very quickly, and then it starts to go up slowly again, yes? So this curve is very, very typical of when we have a strong acid and we are dripping into it a strong base. Down here, we have excess acid. Right in the middle of the vertical section, what did we pick when we are right in the middle of the vertical section? We have picked the equivalence point. Yeah. Middle of the vertical section is our equivalence point. And if we have a strong acid and a strong base together, what pH do you imagine that? Yeah, that's at pH 7. Okay, so that's going to be pH 7 right there. So down in this portion of the curve down here, we have excess HCl, say. Up in this section of the curve, we have excess NaOH. And in the middle of the curve, what species are present? Yep. Na plus, Cl minus, and water. So we essentially have a salt and water. What can you say about the Na plus ion in water? It does not hydrolyze. And the Cl minus ion does not hydrolyze. And therefore, the pH is 7. If you had hydrolysis of the salt, then your pH at the equivalence point would not be 7. Okay, but in a strong acid, strong base, those species are always going to be the conjugate acid and base of a strong one, so they can't, hydrolyze in the backwards direction. Does that make sense? Yeah, okay. So that S curve is what a strong acid, strong base looks like. La, 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 strong acid, strong base. We have the equivalence point. Oh, could you tell me the concentration of the acid at the beginning? Oh, 0.01 molar. How'd he do that? And we know that the pH is 2, and therefore 10 to the -2. Yes? Okay. So there's a lot of rambling on in here. As NaOH is added dropwise, H3O slowly starts getting consumed by the hydroxide and producing, and the analyte is still acidic due to the unreacted H3O+. This point right here is just before neutralization takes place. This is just after neutralization takes place. And at the equivalence point, all you've got, like you said, is that salt and water, and they do not hydrolyze, and so we are at pH 7. After that point, after the equivalence point, you are simply adding hydroxide. Yes, because you are adding sodium hydroxide, and so that's what makes the pH so high once you get past the equivalence point. So you've got that excess H+ at the beginning, you've got neutralization and a salt that does not hydrolyze, and then you have hydroxide. Is good? Good. Moving on. Oh, look, we already did that question, so we're going to skip that. Here is a question that lets you use some data here. What volume of NaOH would be needed to reach the equivalence point if the concentration of the added base were 0.200 molar? Now let's just take a quick look here. This actually says that the diagram is 0.100 molar NaOH. So we have 50 mils of 0.1 molar HCl. And we know that the concentration of the NaOH for this diagram is 0.1 molar, because that's what it says in the question. This is the pH curve for the titration of 50 milliliters of 0.1 molar acid with 0.1 molar NaOH. So, because they are both 0.1 molar, yes, does it make sense that the equivalence point takes place at 50 milliliters when we have 50 milliliters of the NaOH? Yes. Now, what would happen to this graph if instead the concentration was of the NaOH was 0.2 molar instead. What would change about that curve? Tell your partner, chat with them. What do you guys think? Yeah, you would half the volume because you have doubled the concentration. It's going to take half the volume to get to the same point because that will be that'll give you the same number of moles. Yes, because if we look at this one here, this gives us what, 55 millimoles of NaOH. And if we have here, if we have 25 mils to the equivalence point, that also will give us 50 millimoles. 5 millimoles. That's what I said, wasn't it? Millimoles. Sure it was. Okay, is good? Okay, now let's take a look at the species that are present here. When we first start, we have only HCl present. Yes? Only HCl. When we get to halfway to the equivalence point, we have used up half of the H. We have neutralized half of the H, yes? And when we get all the way to the equivalence point, we have neutralized all of the OH. So we would have an H2O here that wasn't there before, yes? And we would have an H2O there that wasn't there before. And then afterwards we have excess hydroxide, okay? So it's just a nice little picture saying what we've been saying in words. Okay. This is the titration of a strong base with a strong acid. Guess what? It is just upside down, okay? So in this case, what would be in our burette? And what would be in our flask? Yeah. The base would be in the flask, and the acid would be up here. Okay? So there's nothing really different about that because it's strong, and strong, the pH at the equivalence point will be 7. Because when you titrate a strong acid and a strong base, the salt that is formed does not do what? Hydrolyze, okay? Because we have HCl plus NaOH goes to NaCl plus H2O. It doesn't matter who's in the burette and who's in the flask. The product of that is this salt, and neither Na plus nor Cl minus hydrolyze. And therefore the pH is 7 at the equivalence point. So when you're drawing these curves, you want to make sure that your slope in the beginning part is very shallow. It's not flat, it is going down a little bit, but it's very shallow. And then it does this steep part. The middle of the steep part, of course, is the equivalence point, and then it is shallow once again. Okay, now we get into the exciting part. Titration of a weak acid with a strong base. Let's take a look at this curve and tell me if you can see things that are different about it from a strong curve. There are a few things that are different. Pardon me? The equivalence point is not at 7. The P equivalence point is greater than 7. Yes, Casey. A little whoop. Yes, that is intentional. Okay. There's a little hill. I call it the hill. And actually, there's a reason that I call it the hill, and we'll get to that in just a moment. Okay. No, there's not a reason I call it the hill. I don't know what I'm talking about. There's the reason I call it the hill is because it looks like a hill. I wanted to say something different, but I didn't say that. Okay. So those are two things that are different. And also what you'll notice is that the vertical section is shorter. Okay, so we have a shorter vertical section. And the equivalence point is not at 7. Now, this is our substances here. We have NaOH and we have CH3COOH. Who do we have when we have neutralized NaOH plus CH3COOH? What do we get as our product? H2O, NaCH3COO. So at the equivalence point, the species we have are water. Do I even need to write water? No. What do I have? Right when it's been perfectly neutralized, I have a salt, which is Na plus, and I also have CH3COO minus. Yes? What does sodium do? Nothing. No hydrolysis. I'm just going to put hydrol. What does CH3COO do? Hydrolysis. So even though you might think, oh, I've perfectly neutralized my acid, that is true, you have perfectly neutralized the acid, but you have created a salt that contains a basic anion. Yes? And so what is it going to do? It is going to produce hydroxide. Yeah, it'll accept some protons from the water and it will leave you with hydroxide. And that's why the pH at the equivalence point is higher than 7, because the salt will undergo hydrolysis to produce hydroxide. And that's probably written down here somewhere, so I'm not going to try and cram it in here when I know it's going to come up later. Okay. So at point number 1, there is no NaOH added yet, so the pH of the analyte is low. One other thing that we didn't notice is that, do you remember how in our last one the pH was 2 at the beginning? Here it's not 2, it's 3. And that's because you have a weak acid instead of a strong acid, so it is less dissociated. Yes? Nope. Not that I know of. I mean, there are solubility titrations, which is a different beast altogether. Yeah. You wouldn't choose to do an acid-base titration when you had other reactions going on the side. That would just be sort of counterproductive. Yeah? So, since acetic acid is a weak acid, it's only partially dissociated, so there's less H3O plus than when we had the HCl, and that's why this is a higher pH at the start. Since CH3COOH is less dissociated than HCl. Higher. Yes, because it's less dissociated, we have less hydrogen, and so the pH is therefore higher. Now the interesting bit is when we have at the very start, we have not so much H3O plus, right? Here's our CH3COOH. We have that much H3O plus as opposed to this one, which has all converted into H3O plus. Make sense? Okay, cool. Between points 1 and 2, as NaOH is added, the H3O plus slowly starts getting used up by the OH minus. Okay, and we're going to keep going here. We've got the same drawing again, so we can still refer to it. In this section here, what species are present in that section? Yeah, we still have CH3COOH. And we have some H plus, and we have some CH3COO minus, because we've turned some of it into the CH3COO minus. Does this put you in mind of anything that we might have talked about earlier today? We have a buffer. We have a weak acid and we have its conjugate base. And in fact, when we are halfway to the equivalence point, that's why there's a little bit of a curve at the beginning, is because we don't really have that like conjugate base thing happening yet to kind of push the equilibrium backwards. At halfway to the equivalence point, the pH is equal to, guess what? The pKa plus the log of Ba. And at halfway, those two would be equal, yes? And so pH is equal to pKa at the halfway equivalence point, okay? So right here, pH is equal to pKa. So if you are doing a titration curve and you are asked to find the Ka of the acid, you can use that half equivalence point to find your Ka. Yes, you just read off what's the pH here. You could be like, okay, what's the pH there? That looks like about, what, 4.2? Okay, so we'll say 4.2. Which means that our pKa is equal to 4.2, right? And if that's the case, then our Ka is equal to 10 to the negative 4.2, which is, let's see, 6.3 times 10 to the minus 5. Now, the actual value, if you read it on your table, is 1.8 times 10 to the minus 5. But reading off a graph, you might not get super, super duper accurate results, right? Anyway, yeah, so at our equivalence point, so two really important points. I keep like rambling, sorry. Halfway equivalence point is important, equivalence point is important. Yes? So your equivalence point is higher. So this is like what, pH of something like 8.3? Why is that equivalence point 8.3? Why are we getting that basic? Yes. Oh, about the previous question, yes. Where? This one? Yeah. How do I know that those two are equal? Ah, very good question, very good question. So when I have gotten halfway to the equivalence point, what that means is that I have neutralized half the acid, okay? So I have in my thing, I'm gonna not write any of it undissociated because the amount undissociated is so small as to be meaningless, okay? So I got HA, 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 HA. I'm just gonna put 4 particles in there, okay? If I add 1 OH minus, then I'm going to end up with an A minus. Yes? If I add another OH, I'm going to end up with another A minus. Now I've neutralized half of it. So I am halfway to the equivalence point. I'm really glad you asked this, because I did not make that clear. And if we're halfway to the equivalence point, then our concentration of HA is equal to the concentration of A because we've taken half of it and converted it into A. Is good? I like diagrams with like 4 molecules. They make me really happy. I can deal with that. And that's why the pH is equal to the pKa at that half equivalence point. All right. So back to our other question. Why is the pH higher than 7 at the equivalence point? What is in our beaker at the equivalence point. Yeah, I've got CH3COOH because all I've got left, like everything has turned into A minus, yes? Which in this case is CH3COO minus. And that's what would happen if we took this and just continued neutralization. So if we continue our neutralization, we end up with all the HA being converted into A minus. So all we have left is A minus, so all we have left is CH3COO. What can happen to the CH3COO? It can hydrolyze. So it's due to hydrolysis of the CH3COO minus. Ooh, that's a typo. So what's the pH? About 8.3. Who are the ions present? Sodium and acetate, CH3COO minus. Do they hydrolyze? No. Yes. CH3COO minus then reacts with the water. What do we get as our product? CH3COOH and H3O plus? No. Why not? Because our CH3COO accepted a proton, what are we left with? OH minus. If we are left with OH minus, is our solution acidic, basic, or neutral? It is basic. Now, you'll often get asked this question. You have titrated a weak acid with a strong base, what we just did here. And they'll ask, why is the pH at the equivalence point greater than 7? And people will say it's because the acid was weak and the base was strong. Therefore, the base overpowered the acid. That is not true at all. They just react in a one-to-one fashion. Yes? It doesn't matter whether it's weak or strong, they still react one-to-one. Yeah? What matters is that the salt that you make is either going to hydrolyze and you'll end up with a basic solution here, or if you were doing a weak base with a strong acid, it would be an acidic solution. Or you produce, with a strong combination, you produce a salt that does not hydrolyze and you have a pH of 7. So at the equivalence point, you should always be saying, who is my salt? What happens to that salt? That's what's important at the equivalence point, is what is happening with the salt. So here we are after the equivalence point. What do we have? We mostly have OH minus, which is why, again, if you compare, here's an actual side-by-side comparison of our weak acid strong base and our strong acid strong base. You can see all those differences we highlighted before. But after the equivalence point, those curves are the same because the pH is predominantly affected by the OH from the NaOH. Does the salt hydrolyze a little bit and add a little bit of OH to that equation? Yes, it does, but it is so minimal in comparison to the amount coming from the strong base that we can just ignore it. Yes? So the vast majority of the OH is from the excess NaOH. OH minus from the hydrolysis of CH3COO minus is tiny in comparison. So if you want to know the pH after the equivalence point, just calculate how much NaOH is in excess and then divide by that by your total volume. Yes? Yeah. Well, the nice thing is that you're going to, do you see how it shoots up? The volume is very similar whether you're at the beginning of this curve or at the beginning of the vertical portion or the end of the vertical portion. The volume is still 50 milliliters. So as long as you're hitting it fairly closely, even if you're out by a drop, you know, if you're out by a drop this way or a drop that way, and I've drawn those drops as being incredibly huge compared to what they would be, you're still really close to the volume. And so your calculations of the number of moles will be really, really similar. Yeah? Yeah. And that's why it's so nice that it has that like really steep portion, because, you know, it's pretty much the same. Okay? Sorry, what was that? Yes. Just by the volume. Yeah. Yeah. Okay, so that's our equivalence point, is that volume. And then for looking for the pH of the equivalence point, you would find the center of the vertical section. So the equivalence point, the volume is right where that vertical section is, and the center is where the pH of the equivalence point is. Yeah? So to find the concentration of OH after the equivalence point, that's going to equal your moles of NaOH in excess divided by your total volume. So that's very much like, you know how we did those mixtures of strong acids and strong bases, and we said, what's the pH after we mix these two? And you calculated how many moles of this was in excess. That calculation would be the same, because at that point you can ignore the fact that, yes, once upon a time there was a weak acid there, but we've now neutralized it all. And the weak base that we produce, we don't really care about it because it's not producing a significant quantity of hydroxide. Yes? Cool. All right. So here are some lovely pictures. Okay, you can see we have all CH3COOH. Of course, there's a little bit dissociated, but not enough to make much of a difference. Yes? Then we add OH, and we have converted, so we have half is the CH3COO minus, and half is the CH3COOH. And when you're in that section, what section are you in? You are in the what region? The buffer region. Yes? And you'll be in the buffer region both below and above that halfway point. You'll notice once you come out of it, you're starting to come out of the buffer region here, right? Because it's starting to pick up, right? And you didn't get into it until you're about there. Okay, you don't really need to like know how to find those volumes. You just need to know to look at the curve and say, oh, look, that's where it's staying fairly constant. That's where it's sort of flat-ish, okay, comparatively to the regions around it. And then, of course, we have all CH3COO minus. And that hydrolyzes. And then we have XSOH, and that is our predominant species that affects the pH. So once again, we're going to look at this and say, okay, we have 50 milliliters of 1 molar acetic acid. So this curve here is for 50 milliliters of 0.1 molar acetic acid. And we are titrating it with 0.1 molar NaOH. What would happen to this curve? What would happen to the volume of base needed to reach the equivalence point if we now have 0.200 molar HCl instead, if that replaces the acetic acid? What's going to happen? Oh, I'm sorry. That should say 0.1. I'm changing two things. That's no good. 100 molar HCl. Huh, my apologies. I don't know, would it be the same? Chat amongst yourselves, would it be the same? Would it be different? Now I have a strong acid. Why do I have so many of these? Okay, people aren't taking it. That's okay, as long as people have left them, that's all we need. Okay, it's all good. What do we think? Is the volume to reach the equivalence point going to be the same? Is it going to be different? Is it going to be more, less, what? Less? Why? Because okay, but I'm adding NaOH. How much NaOH do I need to reach the equivalence point? We're going to vote same, different, more, or less. So have one final last chat. Is it going to be the same? Is it going to be different? Is it going to be more? Is it going to be less? Actually, I should just say same, more, or less. Okay. What do we think? Is it going to be, oh, they're still talking. We'll give them a minute. No, don't be sorry. You should be talking. That's good. You want to convince each other. Nicole, have you convinced anyone? Only yourself? Oh, you convinced Eddie. Okay. Eddie, did you convince Nicole? An agreement? Excellent, excellent. Okay. All right, my friends. Okay. What kind of an arrow do I get when I react to strong acid with a strong base? One way. What kind of an arrow do I get when I react a strong acid with a weak base? One way. Because the hydroxide just rips the hydrogens off. It doesn't have to wait for them to dissociate. It just rips them off. Yes? So yeah, they are going to be the same because it is still one hydroxide for one hydrogen. So beware of that little thing. A lot of students will say, oh, it's weaker and therefore it requires less. Or it's weaker, therefore it requires more to rip off its hydrogens. No, they just react one-to-one. The strong doesn't care what it's reacting with. It will just completely react whatever it has been put with. Okay, so it's going to be the same. The weak, it doesn't matter what the strength of the weak one is. always goes to completion. Yeah, yeah, yeah. Any strong plus weak combination will go to completion. Any strong combination will go to completion. Any weak combination will form an equilibrium and would be useless for doing a titration, right? You would not get data that you need for a titration. A titration has to go to completion. Otherwise, it's useless for figuring out, you know, what the concentrations are and all that. Okay, so it will be the same. What would happen to the equivalence point if we used HCl instead of acetic acid? It would be at 7 instead of above 7. Okay, very good, very good, very good. Okay, what does that say? Yeah, that's fine. How does the pH at the equivalence point change as the acid being titrated becomes weaker? So we'll take a look at this. How does the pH change as the acid being titrated becomes weaker? You'll notice they all take the same volume to get to the equivalence point, yes? But as the acid becomes weaker, what can you say about the pH at the equivalence point? And I'm going to zoom in here so you might be able to see these. You might find it easier to look at your page because the numbers are quite small. We have 10 to the negative 2, 10 to the negative 4, 10 to the negative 6, these are our Ka values, and 10 to the negative 8. And down at the bottom, we have a strong acid whose Ka is just very large. Okay, what happens as our Ka value gets smaller, as our acid gets weaker? The pH at the equivalence point gets higher. Yes, because you can see here, this is the weakest of the acids, and its pH at the equivalence point is the highest. And that's because the conjugate base, which is what you have, is stronger. So it produces, so when it hydrolyzes, it produces more hydroxide. Okay. But you'll notice what about the volume it takes to get to the equivalence point? The volume is all the same. As long as the concentrations are the same. Are we going to finish? 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 Let's find out. Do we need this for another minute? I'll leave it there. Let me know when I can scroll. Casey, yes? Nope, because you would form an equilibrium, which means you don't go to completion, which means you can't figure out how many moles are needed to completely react with how many moles, because there is no complete reaction. Yeah? Yeah. You can do lots of other things with weak acids and weak bases, like form a buffer and, you know, set up interesting equilibria, but you cannot do like a quantitative titration because you need that to go to completion. Yeah. You could look at the pHs, but you wouldn't really do a titration per se. Yeah, but you could definitely do a graph of the pH, which would be interesting. Okay, but titrations are generally in order to figure out concentrations or, you know, mass present or something like that. Now, here we go. Here we have a weak base with a strong acid, and you'll notice it looks just like the weak acid with the strong base, except for it's all upside down. So now, instead of our hill kind of curving upward, the hill curves downward. At the half equivalence point, we have our pH. Yes. If you convert that to a pOH, that would be what, 14 minus 9.24, 4.76. What could we figure out from that at our half equivalence point? We could figure out the pKb. Yes. Yes, because remember, pOH is equal to pKb plus the log of AB. And at the half equivalence point, A is equal to B. And therefore, pKb is equal to the pOH. Yes. Now, what do we notice about our equivalence point? It's below 7. The equivalence point is less than 7. Why? And here we are titrating NH3 with HCl. Yep. Okay, so at the equivalence point, all we have is NH4 plus and Cl minus. And the NH4 plus hydrolyzes to produce hydronium. And therefore the pH is less than 7. Is good? Okay. What would the initial pH be if the base in the flask were 0.1 molar NaOH instead of 0.1 molar NH3? Seven? The initial pH. Initial pH. And I'm messing with you a little bit here because when we initially, what do we have in our flask? 0.1 molar NaOH. So if we have 0.1 molar NaOH, what is our pH? That would be our POH, would be the negative log of the concentration of OH. So we would have the negative log of 10 to the negative 1, yes, 0.1, which would be 1. And so therefore our pH would be 14 minus 1, which is 13. So an initial pH of NaOH is 13, and the initial pH of the NH3 was 11.12. Why is the initial pH of NH3 lower than the initial pH of the NaOH solution of the same concentration? This is not a rocket science question. It's pretty straightforward. This is not a strong base. It does not ionize completely. Therefore, lower H, therefore higher pOH, therefore lower pH. Excellent. Okay. We already wrote this. NH3 plus HCl. These ones always look a little bit weird, but because as long as you remember that they are just Bronsted-Lowry reactions, then it's not so bad. When the equivalence point is reached, what are the only species present? Now I'm just repeating myself. What are the only species present at the equivalence point? NH4 plus and Cl minus. So we ask ourselves, who are the ions? They are NH4 plus and Cl minus. Do they hydrolyze? Yes, no. Hydrolysis equation. We've done this already. I don't know. That's why I don't do so well with scripted notes, because I get excited and I write things down and then I realize my script has it later. Anyway, NH3 plus H3O plus. Is that acidic, basic, or neutral? It is acidic. Oh my God. Okay, the answers are there. Blah, 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 blah. And now we're into exercises. Oh, yes. Okay. So we finished that. We have one last thing to do. Can we do it? We have 10 minutes. We can do it. Yes? Yes. And then we'll be done acids and bases, other than like one little AP thing that, like, it's tiny though. It's really tiny. It'll take us like 10 minutes on Monday. Okay? So, oftentimes, that looks weird as one word. Maybe it should be 2 words. Oftentimes in an acid-base titration, an indicator is used rather than a pH meter. Optimally, an indicator should change color at the pH of the equivalence point. Yes? So for a strong acid, strong base titration, the pH at the equivalence point is 7, which would suggest that we use bromthymol blue, which changes color from pH 6 to pH 7.6. Yes? Now, you'll notice when we did our titrations, we did not use bromthymol blue. What did we use? We used phenolphthalein, That's the one that turns from colorless to pink. This one is a yellow, bromthiamyl blue is like a yellow-blue one. Why might it be nicer to use something that goes from colorless to pink rather than from yellow to blue? There's no gray area. It's either like it's not pink and then it's pink, yes? Whereas with bromthiamyl blue, it's like, ooh, it's green. Is this the right shade of green, right? Should it be a greenier green? Am I at my greeniest green that I could possibly be at? That's a little bit harder. Why does it still work to use phenolphthalein to find when we have hit the equivalence point? Yes? At that one volume, it's in that huge range of pH when it just shoots up, right? So within one drop, you're going to go from here to here, and it doesn't really matter what you hit in the middle. It's still going to tell you that the volume is 25 milliliters to get to the equivalence point. So you really want to make sure it changes color within the vertical range, okay? So the indicator must change color within the vertical part of the graph. So anywhere within that vertical part and you're good to go. So I mean, there's some examples, right? You can see bromphenol blue is kind of like the first one that might be okay. Bromthymol blue is fine. Phenolphthaleine's fine. Alizarin yellow, you know, it might be, you're getting close to a danger zone there, yes? Because you can see the pH is starting to now, our volume is starting to change a lot. So I would say like bromphenol blue is sort of, again, it's almost in that danger zone. Tend to go with something in the middle of that range. And you definitely don't want to be using methyl violet because methyl violet changes at pH, you know, 1.6 or so, right? Or pH 0.8 to 1.2 or something like that. And that would tell you that your equivalence point is at 12.5, which it obviously is not. Yes? So there's a lot of like rambling on here, but what is an endpoint? Just remind me, what is the endpoint? It's the point in a titration where indicator changes color. And the equivalence point in the titration is the point where the reaction is complete with no excess of either reactant. Sometimes I like to say where the stoichiometry has been perfectly fulfilled. So here we have a lovely little picture. If we are titrating a weak acid with a strong base, remember we get the little hill. First comes the hill. What comes after the hill? The buffer zone where it's going up, like shallow. And then we get the vertical portion. What's in the middle of the vertical portion? The equivalence point. And what is dominating the pH once we get past the equivalence point? Whatever you're adding, yes? So if you're adding hydroxide, it'll be the hydroxide from the sodium hydroxide. If you were doing it the other way, it would be HCl maybe, yes. Yes, always right in the middle. You just look and you put it right in the middle. Yep. Okay, and then we have, which of these indicators would be good? I think that's pretty obvious, isn't it? Phenolphthalein definitely works because phenolphthalein changes from 8.3 to 10, and that is right nicely where the equivalence point is. Methyl red changes from 4.2 to 6.0, which is happening here, right? From there to there, and sort of the midpoint there would be there. Oh, that doesn't look so good, does it? Okay. So that's really all there is to that. And then there's some exercises. So on the weekend, these exercises are pretty short. So why don't you do them, I think. Let's just make sure they're quite short. Stop bouncing your damn ball, kid. Oh yeah, they're short. So pages 81, no, not 81, pages 82, 83, and then also 87, 88. Now, if you are feeling like hydrolysis is not so awesome for you at this point, could you go back and do some of the extra hydrolysis problems? Yes, you could. If you are feeling like you need some extra help with, if you're not so sure about buffers, actually it wouldn't be the worst thing in the world to do just a little bit of buffer stuff, sort of the, excuse me, the more generic stuff. But if you just want to get down to studying the overall thing this weekend, that is also fine. I would like to have our test on acids and bases next Thursday. Okay? Well, when else are we going to do it? Right? If I put it off till the next week, then you don't even have a week to study the overall stuff, right? So let's say it's next Thursday, and you know what? If this test tweaks you, then maybe we'll look at it not coming for a month or something. You know what I mean? Because we're sort of having everything, right? It's another one of those ones where it's like the situation is not ideal, right? But how do you make it ideal? Yeah. I used to, when I first started, I was so not looking at it like at the end. I'm like, oh, great, we're at the end. So much more time to study for my exam. You know, we don't study for it until all the other exams are done, and then we study for that. Make sure you study for all your exams. All of them. More than one. Yeah. Yes. Yes.
And also, I'm pretty sure